Okay, everyone. This time we're going to just be working on pretty much the exact same presentation we were looking at last time, except this time we're going to intersperse it with some code examples. First with an example of Python and then PyTorch. So what we're going to do is going to look at sort of the basics of deep learning from the Perceptron again, and then all the way up to the Autoencoder. And I'm happy to say I think we have a winner for the Autoencoder challenge I put out last time for $50. And Dave, are you on?
Yeah, I'm on.
Okay. Maybe we can give you a little bit of time when we get to that challenge and you can talk to your solutions, but you had 160 solutions, so great job. I'm going to look through those, but you were the only one that sort of submitted, so great job. And I look forward to looking through all those solutions and stuff like that. Did you try any solutions by using the 2 values at all?
Sorry, using the which values?
The weights of 2. So using a weight of 2 value.
There, yeah, in some cases where one of the weights had to have a minimum value, so it could go up all the way up to 2. It wouldn't make a difference because of the step function and the activation. But yeah, I think those are the only situations where I used. No, actually, there's one other situation I think I used 2. But.
Okay, awesome. Yeah, great job. Okay. So as I said, we're going to go over the pretty much the exact same thing. We're going to talk about the learning problem again. And I think most of you, or a number of you were here last time, but I'm going to go through this again. We're not going to play the games, but we're going to look at code examples. So again, you know, when we're developing a machine learning problem, we always sort of look at our inputs X and look at the predictions Y. And this type of model is called the supervised learning model. We went over that last time. And the basic model we typically deal with, or the first model you'll deal with when you're doing data science, is a linear regression model. So you'll fit this sort of line to a set of data points. If you used Excel, you'd probably use the same thing, obviously. Okay. So basically, what we're going to look at is the Perceptron encode. We're going to start with how the Perceptron can be implemented in Python code. And again, this is the Perceptron that was inspired by essentially connectivism in the brain, how our neural pathways connect and stuff like that was the inspiration for deep learning itself. Okay, and then there's sort of the summation function and how a Perceptron works. Is there anybody here that didn't cover this before in the last session? And if you go under participants, oh, I don't have it on. I thought I had the feedback option on, but I guess I don't. I was going to ask some questions of the group, but don't worry about that. Okay, so again, the simple Perceptron, the weights come in. Our top weight is always our bias, and then our weights come in are multiplied or scaled by the weight itself for the input. Those are pushed through a summation function, then the activation function modifies the output in some form, and that goes to the output. Okay, so that's our basic Perceptron. That's what we covered in our last lesson. And here's the Perceptron game. So if you didn't get a chance to play it, there's the URL. You can go there and just play the game. The basic premise of the game is just to classify these 3 images by balancing the weights. So we won't really spend any more time about that. And the simple solution for this is just 0.5 and 0.5. And on the activation function for this simple Perceptron, there was really no activation function. It was just a linear activation. Okay, so let's just going to jump into some code here. Okay, so if we go to my GitHub repository, you can all go there. It's cxbxmxcx at GitHub, or I'll just paste the link into the chat window. Okay, so there's the repository for all the code. this will be all the code for the book that's going in there. So, I mean, you can look ahead here, but what we'll be generally going through is chapter by chapter through each of the sessions. We might break up one chapter over 2 sessions, or we might be able to, like this session here, we're going to go into a little bit of the second chapter just for the autoencoder example. So when you go to this page or this repository, you'll see all the code links. You can just click on one, and that'll take you to the GitHub repo, and you'll see at the top here, there's this blue button. You just have to click that blue button and it'll open the notebook in Collab. And then from Collab, you can just use the model to train it on your own in a browser by yourself. So here's our first example. And what we're going to do is look at a Perceptron. And this is just straight Python, and it's the XOR problem. So the XOR, again, is just that truth table, right? And here we have it set up in a NumPy array of values. And our first set of values is 0, 0, 0, 1, 1, 0, and 1, 1. And if we refer back to the XOR truthy table, the 0, 0 gives us 0, 0, 1 gives us 1, 1, 0 gives us 1, and 1, 1 gives us 0. So an exclusive OR function essentially is all we're training. And all we're doing is entering our data sets into 2 NumPy arrays. And we'll use NumPy a lot for handling tensors. And again, tensors are sort of multidimensional matrices or multidimensional arrays that we sort of jam all our numbers into that we push through our model. And tensors could be either CPU or GPU bound. In PyTorch, there's two definitions you can set up. So a lot of for this session of the meetup here, we're just going to look at CPU bound tensors, but as we get into more complex examples, we'll start to look at GPU bound tensors. And the difference between CPU and GPU bound tensors is just the way they're processed or which part of the computer is getting processed. So when we have GPU bound tensors, we can begin to take advantage of GPU processing, faster computations and stuff like that, and that'll speed up the notebooks quite considerably. In order to do that, though, we have to turn our runtime on, and there's a little setting here if you click on the option to change the runtime type. And you can see here I have hardware acceleration set to none. Some of our notebooks, a bunch of our notebooks in the future will be set to GPU, and that's typically almost 100 times faster, depending on what you're using, what types of layers or pieces you're using, or faster. We won't use a TensorFlow processing unit because we're using PyTorch. We'll just stick to GPUs for that case. Okay. So again, this example we're currently looking at is just Python. So when I print out the X shape, this gives me the shape of the tensor. So you can see the X, or the input shape here, is 4 by 2. So there's 4 elements, all of them 2 in size. And our Y shape or predictions are just an array of 4 elements, right? So that's what the NumPy print is doing there. And then I'm going to plot this. So I'm just going to look at using matplotlib, which will be a common plotting library we'll use for a lot of our things to show outputs or figures or images and stuff like that. So in this case, I'm just grabbing a figure from plot figure. And if you're having any troubles understanding some of these imports and stuff like that, let me know, and maybe I can go a little slower, or we'll just see what the sort of interest level of the grouper is, or what the experience level of the group is. I'm just making sure nobody else is waiting in the waiting room. Okay, so what I'm basically sort of plotting here in 3 dimensions is the points, because the points in this solution or this problem are not linear, right? If we plotted them on a linear line, 2 of our points would be at the same point, essentially. So when I plot them in 3 dimensions, I can see all 4 points at different segments. And you can see that's part of our problem, is that from a linear solution, we don't really have a good single line of fit through all 4 points. And that's part of the XOR problem with a single layer of neural networks or deep learning. Okay, so if I go down to the next block here, you can see my number of inputs is equal to the shape of our first element, which again is, the first element is 2, remember 0 is 4. And then our weights, we just sort of randomize. We're using a NumPy function called random, and random just for the number of inputs. And remember, our number of inputs are 2, but because we always add a bias when we're looking at perceptrons, we add 1 in this case. And then if I print out my weight shape, you can see there's 3 elements there. So in this case, we're looking at 3 elements, not unlike the Perceptron game that we were looking at before. Okay. So then in here, what I'm doing is I'm just doing a quick loop and going through some of the input solutions. And I'm just seeing what, using those random weights, what they're randomly set at, what the outputs are. And you can see these are just random outputs. There's no training here at all. And when I run this, 0, 0 is giving me a value of almost 1, which is entirely incorrect. And 0, 1 is giving me a value greater than 1. So this is also incorrect, and so on and so on. So without training, this model is doing very poorly. So this is this very simple training loop here. And you can see our learning rate. And the learning rate, when we apply or use a learning rate for anything in deep learning or machine learning, we're always sort of applying the learning rate as sort of a scalability factor or a weighting factor to how much we're allowing the algorithm to learn through each iteration. So by setting the learning rate to 0.1, we're essentially allowing about 10% of our loss to perpetrate through our network. A lot of times when we're doing deep learning over long periods of time, the learning rate might be really, really small. It might be like 4 zeros here, for instance, right? In this case, it's just a really simple network. 0.1 is sufficient for us. Okay, so the epochs essentially means the number of training iterations we're going to train our network for. And I'm just setting up a loop here to cycle through the epochs, and then a second loop inside that. And I'm using the Python zip function to be able to sort of align our values. And that pulls out the inputs and the label. And we run this through the summation function, which is just using the NumPy dot product. So that's essentially the mathematics behind that simple function that we looked at, or reduces down to a NumPy or essentially vector dot product that will give us the prediction or the summation of those values. Now, in this case, again, we're not using any activation function, so we're not sort of passing anything through an activation function. So you can see our loss essentially is just a simple label minus prediction, right? And we're appending that to a history array that we can sort of look at later. In this case, we're just sort of taking the loss times loss to look at that, what the value is. There might be other different ways we're calculating loss. We'll get into that later, but this is just a simple label minus prediction loss is what we're doing. And then based on that loss value, this is the loss we're pushing back through into the weights. So that essentially the very simple adjusting the weight function here is just taking the loss times the inputs and applying that back to the weight, as well as for the bias as well. And remember, the learning rate here is applied as sort of a scalar or a multiplier to reduce the amount of changes we're applying. And we'll look at why we want to reduce this. So what I'm going to do is I'm just going to quickly go up to runtime, run all, so I can just run the whole sheet. You can also, if you want, just click each of these little buttons to run each of these things if you're a little less familiar with Python notebooks. Chances are, if you've done Python programming, you've probably looked at zoom the screen in a bit. Here, sorry. Okay, how's that, guys? Is that fine? Okay. Okay, so from here you can see it's run through the training and it's jumped out a bunch of loss. And what we'll look at is, I'm just going to look at the bottom here. It's essentially dumping out each iteration the loss. And again, running that sort of little cycle through again to sort of test my outputs. And you can see when it's 0, 0, it's not now coming out as 0.5, 0.5 almost again for 0 and 1, and 1 and 0 is almost 0.5. So it's not really giving us a good solution. And you can see with my loss here, I'm getting this almost like this spring or this yo-yo effect. And you can see our loss also minimizes almost around 0.3 or something like that. And that was essentially a fundamental problem with the XOR, because a XOR is only, or a single layer of perceptrons or a single perceptron is only able to do a linear regression problem. This problem is more complex than that. It's actually going to require more layers, essentially, which we'll look at. So I just wanted to sort of demonstrate this quickly. We'll look at another example here shortly, very shortly. Actually, I can just jump into that now. So here's another example of the Perceptron, but this is using a class in Python. It's a little structured a little differently. And in this case, we're actually using 5 data points with 3 inputs into each, and just using arbitrary sort of prediction values. So this is the numbers we want to predict from these inputs, right? Here's my shapes again. So you can see the shapes expanded to 5 and 3 this time. Again, we're using this sort of the plot figure, and we're plotting out our points. You can see this time there's all these points here, the 5 points in 3D. And let me just run all again. We'll just quickly go through these couple simple examples, and we'll go into the PyTorch stuff here. So this is running. So now, in this particular example, what we're setting up here is what's called hyperparameters. So again, we're setting the learning rate. And the learning rate this time, we sort of reduced it a little even further. So we're making it 1% in this case. The epochs, we're turning them down to 50. The number of inputs, again, is going to be set on that X shape of 1. And the weights, again, are going to be set on just that randomized value. And now this time, we're introducing this ReLU activation. The ReLU activation function is essentially cuts off at 0 and then allows everything above 0 through. So it's essentially just like a cutoff function that allows everything through then at a linear scale. Okay. And here's our Perceptron. This is just a simple Perceptron class. And what we're taking here as inputs is the number of inputs and the activation function. And this is just, we're setting the learning rate here, the weights, we're setting at zeros, the activation function. And then we have this function to do the predict and then the train. So in this case, we're allowing the training to sort of happen inside the class. And you can see the training is, again, pretty similar. Our prediction, again, is coming out from the self-predict. So this is what we're calling the predict function. And that's essentially that same function we looked at before. And that's just the math of doing that summation for a single Perceptron. Okay, so that essentially it's a dot product of the inputs and the weights. And then you add the bias essentially. Okay, and then the prediction comes from that self-predict, and we take the loss, again, apply that loss back through. Now, the interesting thing is, our Zor model didn't really perform very well. And this problem, many people would think is more complicated or more complex. But look, as we scroll down and look at the output of the loss, you can see in this case, our predictions aren't too bad. If you see the 333, it's almost coming up. But you can see the loss in this case is still almost going down to 0 in this case, but you still see we're getting this wobble or this almost spring up and down effect. And that some of that is essentially because the function, the single layer Perceptron, or the single Perceptron isn't really able to solve this problem very well. Okay, and we'll look at PyTorch and how we can stack up layers of perceptrons and look at that. But this is sort of a very simple example to demonstrate how all these things work together. And as we look at PyTorch, we're just going to expand on this. We're going to encapsulate some of these things like loss, but it's just helpful to understand that the loss is really just as simple as the label minus prediction. And in this case, the label as 1, 2, 3, 4, 5. And then what the prediction is whatever the weights are, multiplied or dot product with the inputs, right? Plus the bias. Any questions on that? No, I can't improve the streaming quality, and apologies for that. I'll have to look at doing something else later. Okay, so let me just go back to the PowerPoint. Okay, so we looked at those examples, and this is just some useful libraries to learn is what we looked at before. Matplotlib, NumPy, and sklearn for some utilities. We'll look at some other examples where sklearn comes in here in a few minutes. But these are the types of things that'll be very useful if you're doing Python and machine learning or anything like that. These types of libraries will be very useful to just sort of play with and get a little more familiar with on your own. Okay, this again is the Zor with PyTorch. We looked at that. We looked at the Perceptron class with Python. And now we're going to look at, the more complex problems, stacking layers together, or essentially stacking perceptrons, neurons together, so we get, more computational power in our networks or our models to be able to solve these higher order functions that we're sort of starting to deal with. Okay, so again, this is just sort of showing how the loss is determined. So in this case, if we're feeding a cat, an image of a cat through the network, it pushes the input through, it comes up with the loss, and then we push that loss back. Now, as we've seen in the code examples, the loss was a simple matter of taking what the label was and minus the prediction. In some cases, it might be that easy. We'll look at sort of, the autoencoders where it could be that simple. We're just doing a simple subtraction. In other cases, it might be a little more complex. In most cases, though, the loss or defining the loss really depends on what your inputs or outputs are, but pushing that loss back through the network gets a lot more complicated as we layer perceptron or layers of perceptrons on top of each other. And that gets back into, solving that equation. And this is that forward propagation equation that sort of gives us, essentially that's the unfolded equation of the forward pass through a neural network that needs to be solved for the weights to determine how much influence each weight needs to be adjusted. So with a single perceptron, you see the equation was fairly simple. As we sort of layer these things on top of each other, they become far more complicated. Okay, and again, here is that calculation of loss. So this is the first equation here is the calculation of forward pass. Then we sort of rewrite this as a function, apply the chain rule. That gives us the ability to differentiate with respect to, for instance, first we do with respect to the inputs, and then we do with respect to the weights. And then by determining the differentiation with respect to weights, we can essentially determine how much of what's called a gradient or amount of direction and amount we can change that weight to train it to a value that sort of aligns with what we want to train it through for the data that we've shown it. Okay, won't need to go over that too much. So again, that's pushing the loss through. We can talk to stochastic gradient descent. We'll look at that as some examples or other optimizers as well. Okay, now this is the multi-layer perceptron game. If you want to go back and play that, this will give you a demonstration of how this sort of works. And you can go through and play and try and adjust the weights on your own to try and balance the labels and what comes out as the predictions. We won't go through that too much. But what I do want to cover now is some activation functions. So we are going to look at using activation functions, not necessarily step or full step functions, but we'll look at sigmoids and tanh functions and stuff like that. The ReLU, again, is sort of that linear piece, but as it comes to zero, it sort of flattens out in a straight line. Okay, so that's what that ReLU function is we looked at earlier. Okay, we won't look at that. We're going to go back now. We're going to look at a multi-layer perceptron using PyTorch, and we're going to look at the Zor problem again. So let's just jump back. Okay, so this is the Gen 1 MLP PyTorch example, and this will be our first exposure to PyTorch. So I'm going to go through a few pieces here. So the imports you'll see are a little bit different. Again, we're doing some importing in the NumPy, and we're importing Torch and the other Torch libraries. Now, one of the other reasons why I like using Google Colab so much is I don't even have to worry about installing these or worrying about the proper versions in most cases, because Colab has PyTorch, all the correct versions of PyTorch we need, so you don't have to do a lot of worry about setup. And PyTorch used to be quite complicated to set up. It's gotten much easier if you need to set up on your desktop, but for Colab, it's so easy just to you just have to put a block in here like this to run it. So let me just run this whole sheet again so we don't have to worry about that. I'll just go through and keep running. So in this example, we're using a class of XORnet, but now I'm using a number of functions from PyTorch. And the first one is called a linear. And you can see as I hover over it, it's giving me sort of some comments from the actual application. And you can see linear applies a linear transformation, essentially the same as perceptron or a single layer. We often refer to them as a linear or linear transformation layer. And in this case, we're taking 2 inputs, and this is pushing down to 10 neurons or 10 sort of nodes you can think of. And then we're adding another layer, and that layer again starts with 10, because remember these 2 layers are joined on top of each other. Okay, so we have 10 up here, 10 down here. We have 2 inputs coming in, and then from the bottom, you can see we have 1 input coming out. Okay, so from that, and you can see through here that we're also using this functional model from PyTorch that allows us to use various activation functions. So we're using a ReLU activation function that's sort of predefined. It's the same as sort of what we already looked at and set up. I just want to make sure. Okay. So the ReLU activation function is being applied. So the forward pass is, again, you can think of, we often call this forward pass now instead of the predict function, but they're essentially the same thing as what we looked at in the earlier perceptron models. So the forward pass is essentially the predict function, and we take the X, which is going to be our input into the model, and we push that through our first layer, and the output of this first layer gets passed through our activation function to X, and that X gets then passed through our second layer, output again, and then we return this value. So essentially we're just returning the raw value. So there's no activation function on the output of this second layer, and that's something to be aware of. So now if we look down, we're setting up our model based on the class of XORnet. We're setting up this loss function based on using the PyTorch neural network. And this is called a mean squared error loss. So this is essentially doing subtraction, but it's just taking the average of subtracting and some squaring the results. And in this case, we're using an optimizer of Atom. And Atom is sort of an advanced form of stochastic gradient descent. It's just a little better model. We'll get into that as we go on through various sessions of the course on other optimizers as we get into other generative models. And the epochs we're using for this example are 500. So essentially 500 training iterations. And you can see here, this is where we're setting up our NumPy arrays again, very similar. In this case, notice that we're not using integers anymore. We actually have to use floats. And that's a requirement of PyTorch. We always want to use floats in I think almost all cases. And then you can see, so our inputs again are the same thing, same truth table. And then, so what we do is, so these are NumPy arrays, X and Y are NumPy arrays. What we have to do is convert them to torch arrays or PyTorch arrays. And so we'll often do this thing where we just torch from NumPy, and that works. This reshape piece here is because the shape of this prediction array just has to be rotated, I guess you could say. And that's just an artifact sometimes. And usually what I say is, oftentimes newcomers, the main challenge you face when you put these models together on your own is sort of understanding how the NumPy arrays need to be aligned or set up in order to fit into the models. And these can be somewhat even more complicated when we're using images or images with channels and stuff like that. Okay, so what we're doing here is we're just setting up a Y train T and an X train T. I'm setting up this history, and so the Y train T and the X train T are essentially our 2 sets of training data. And as we go through, you can see that they are both getting converted again to essentially PyTorch tensors that we can feed into the model. And there'll be ways that we'll look at that we don't have to do this every time, but it's just to be aware that we need to convert our NumPy tensors into PyTorch tensors in order to use them in PyTorch. And again, we're just doing this forward pass, so we're just passing this number through the model, and this gives us prediction. We're using the loss function where we're passing in the prediction and the batch variable, or what the actual label was, and that gives us our loss. And then from here, we're using the optimizer to sort of zero out our gradient, and then we do a backwards pass using the loss to push the backwards pass through the network, and then we sort of do a step. Okay, and these last lines here are ones that you'll see in almost every piece of code we look at when we do training with PyTorch. We'll always do something very similar. We might have a couple of different optimizers, or we might do, our loss might be called something else, but in most cases, we'll do very similar things through our training functions, or our sort of training block of code. You can see here as I go down, now by adding that second layer, I didn't have plot defined, but you can see that by adding that second layer, let me just run this. By adding that second layer, you can see now that if I'm doing a prediction on 1, 1 into my model, it's giving me a value of almost 0, which is correct. And now if I'm giving a value of 1 and 0 into my model, it's returning 1, which is correct. So this model has learned the Zohr truth table almost, at very good results over 500 iterations, just by adding that second layer. Okay, so that was a big thing we're demonstrating here, is how to stack things, how to build up our model a little bit, and basically how the basic code works through here. So do we have any questions on this part? So I'm going to jump into more complicated examples. Nothing so far? Is this all easy for everyone? Oh, got a couple people in the meeting. Okay. Okay. Go ahead.
Yeah. So how do we decide on the number of neurons in each layer? I mean, is that just a random guess?
No, and oftentimes it won't be a random guess, and a lot of times, if you're using newer sort of data sets you're not even sure of, a lot of times it's just going to be dictated by the size of the data, or the size of the example that you're feeding in. So in this case, we're feeding in inputs of 2 inputs with 4 samples. So 10 in this example may be overfitting. Maybe it's probably not underfitting, but it could be overfitting in some cases. So that's where we might go back and we could prune the model, or we might enhance the model. And by pruning the model, I mean we might actually want to reduce this number from 10 down to 6, or we might want to increase the number just to see if it's giving us better results. And we'll get into that as sort of an overtraining or undertraining feature as we get into some more complex examples. But yeah, good question. Thank you. Any other questions? No? Okay. So let's just jump back to...
Mike, just one question. Can you hear me?
Yeah, go ahead.
Yes, Mike. So just looking at that function, like you have used that nn.linear. So I just had a question, like should the input data be linear for this process to work?
No.
Like linearly separable?
No. So no, this is just a linear operation being applied. And so we're applying a linear operation and another linear operation. You can think of that. The data doesn't have to be linear. No.
Okay.
It can, yeah, I mean, that's why we're here. We don't want to work with linear data. We want to work with a lot more complicated data. Absolutely.
Complicated.
Yeah. Okay. So let me just go back to PowerPoint. Okay, so the next one we're going to look at is a little more complicated example, and we're looking at sort of the MNIST classifier. So in this example, we're going to look at training a classification, PyTorch to do classification on the MNIST handwritten digits. And the MNIST handwritten digits collection is a sample of 60,000 images of handwritten digits in 10 classes from 0 to 9. Okay, and what we're going to do is we're going to set up our network so that it can train and understand and sort of how to differentiate those classes just by looking at the images. Okay, so oops. Let me go back to the browser. I'll jump to that example. And this example might seem to be a fair bit more complicated, but it's not really. I mean, there's a few more moving parts, and it looks like, our imports here, they doubled. So this is going to make the example a lot more complicated. And a lot of times, some of these things, might just be importing them, and there's other variations of them. For instance, some of this stuff could be pruned, I guess I could admit, but in most cases, we're just using helper functions, and a lot of these are just setting up things. In this particular instance, on line 6 here, we can see the Torch Vision data sets I'm importing as dset. That's allowing us to sort of look at a number of predefined data sets or training sets that we'll use throughout the meetup sessions to train on a wide variety of data. And it's sort of, you can just sort of grab it quickly, pull it down, and train on it. You don't have to do a lot of sort of modifying the data, trying to understand the data, fixing the data, and stuff like that. So the first thing we set up when we sort of do these pulling these data sets down is a transform. And the transform, in most case, we're just transforming it to the tensor for one thing. But the next thing we're going to do here is we're transforming it, we're normalizing it. So the reason we're normalizing these sort of images, because the images that are coming in are going to be bytes or byte arrays. And what I mean by byte arrays, they're going to be values from 0 to 255. And what we want to do is we want to reduce those values from 0 to 255 to values between either 0 and 1 or -1 and 1. And often in machine learning or deep learning, we want to maintain or normalize our data so that it's close to 1. It sort of gives us the fewest errors, allows us to avoid large numbers or really small numbers in some cases. But we'll often sort of normalize our data that we're pushing to the model. And this is just another example of using that normalization, but we're just setting it up as a transform and pushing it in here. So the first thing we're doing is we're just using this data set helper function, and we're going to load it into a folder called data, again on Collab. And we're going to set this first setup as train. We're just calling it true. We're applying the transform here, and we're just telling it to download true. And again, for the test set. So in this case, we're actually doing a train and a test set. So most data science pieces, and I'm just going to run all of this again. So this will happen if, oops, I didn't want to do that. This will happen if you get too many sessions open in Collab, and you just have to kill some, that's all. Okay, that should be good. Okay, so it should be running. Yeah, it's essentially, you have a number of options for killing or interrupting the execution. So you can interrupt the execution, and that'll essentially keep everything in line. It's just sort of breaking the cell. Or you can say restart the runtime, where it'll just sort of restart everything and refresh. It doesn't necessarily clean out anything that's downloaded or stuff like that. So that's a very useful feature sometimes. Restart and run all, that's also another useful one, just to sort of hit sometimes if you're finding things aren't making sense, or maybe you've done things in the wrong order or stuff like that. That's sometimes very useful. Another very useful thing is you sort of get a lot of errors, you make code changes, and sometimes you want to do a factory reset. And the factory reset essentially means that you're dumping everything that you've downloaded, everything you've stored, everything that's been set up is all going to be reset. And that's essentially what the factory reset runtime does. So from running this block of code, this is doing our pulling down the data sets. You can see it's pulling down from Jan LeCun's site here, pulling those data sets down, unpacking them, putting them in our set. You can see that for our training set, number of data points are 60,000, and our test or validation set number is 10,000, which is quite common. There'll often be a train or test validation set. In most cases, if we were doing this just sort of a raw data science perspective, we might choose numbers. If we had a raw whole big set of data, we might take 80% of that data and use it as training and 20% as test. That's sort of the typical thing we might do. A lot of people might do various different ratios depending on their data, experience, and what they're doing. Okay, and so what we're doing down here is we're setting up a batch size. So everything we've done previously is we've always set one sort of piece of data through our model at a time, and then looked at the results of that. Oftentimes, with deep learning and using GPUs and more performance, when we can sort of vectorize the data into batches, we can take advantage of those NumPy dot products or matrix operations, especially on a GPU. And those give us some really good power. So essentially, if we have a batch of 64 images, we can, a single operation could apply to all 64 images at the same time. And that's really the power of tensors and NumPy and this deep learning stuff, is that power not only from a CPU perspective, so that really gives us a benefit in CPU, but when we apply it to the GPU, and we're using GPU tensors that are happening on the GPU, because the GPU is optimized for matrix multiplications and other things like that, we get a really huge performance boost, especially if your graphics card is, the latest and greatest, or has all these types of things. So first we're going to do is we'll set up some data loaders. And this will be a common pattern we'll use for most of the course. And data loaders are essentially just a way of attaching to a folder or file set, and then giving us batches of that data when we ask for it. And this is sort of a nice piece that we'll do oftentimes. It gives us an ability sort of not to load too much in memory at a time. We only have to load what we need to in memory at a time. So we'll often use data loaders as a way of sort of streamlining the process of how many images we need. If we were sort of maybe doing this on our own, not using data loader, we might load all 60,000 images in memory, which would be a big burden on memory, would probably slow things down depending on your computer or your platform. On a site like this, Collab, I think it does take a lot to run out of memory on Collab. I've had some pretty major applications, and it's like 8 gigs or something like that. I think it'll top out on. So most of these simple applications, we really don't have to worry about this, but it's just really a nice habit to get into, is using a data loader. So down here, I've just defined a helper function here, just to image show, and this is just going to allow us to see what those images look like. And you can see down here, the first thing in line 8 was we're using the iterator from Python to pull one batch from the train loader. So this is a loader we're going to use for training. And from that one batch, we're just going to call next. And that next is going to pull out, remember, from our batch size, 64 images. So remember, this is our batch size of 64. And this batch size we set up on both of our loaders. So that means every time through our training cycle, we're going to look at 64 images at a time from now on. Okay, and we can adjust that batch size as much as we want to or need to. And what we're going to pull out from this sort of iteration is the images themselves and the labels. And then I'm just using this image show and the make grid utils from Torch Vision to generate what the sort of first batch of images looks like. Okay, and you can see there's a set of our example training set. Okay, and the model we're going to look at here is just a really simple multi-layer Perceptron model. In this case, we're using 3 layers. Okay. Fully connected. So the FC stands for fully connected, FC1, FC2, and FC3. And you'll notice here that we're using an input of 28 by 28. And the reason we get 28 by 28 is that each of our images is 28 pixels by 28 pixels. That means our inputs for each of these images are going to be a vector of 784 inputs. Okay, so that's what we're feeding through. And then you can see our second layer is 500 neurons. So we could increase this to 1,000, or we could decrease it. But essentially, we're funneling, as you can see, we're taking this 500 and we're pushing it down to 256, and then we're pushing it down to 10. So we're taking essentially a big flat set of data of 784 pixels, pushing it to our network. And the first layer is 500 neurons, pushing it down to another layer, which is 256 neurons. And then our last set is 10 neurons. And the reason our last one is 10 is because we want to output the class for each of those neurons, right? Because we want to identify what the class is for each of the images. And that's what we're trying to teach our network on, essentially. So again, here's our forward function or our predict function. And this first line here is just a way of sort of flipping the tensor around. We just have to rotate the tensor to get a better sort of the way we pass through. So we're essentially taking these raw images. We're just going to flip the tensor around so that we feed it through the network. It works a little better. In a lot of more of the advanced examples, you don't have to worry about that. The reason why I'm doing that in this case is because I'm taking all 784 pixels and I'm sort of flattening them down and pushing them through. A lot of times in neural networks, you'll use more sophisticated layers like convolutional neural networks, where we could push the whole 28 by 28 pixel image into the network, and then the layer actually uses that full image to extract the contents or features and stuff like that. We'll get into that next section, the convolutional networks and stuff. So you can see here, our first connected layer, again, we're applying a ReLU activation function. Next is a ReLU activation function, or last, again, is passing that last output. And that returns our output. You can see here, setting up our model again as multi-layer perceptron. Our optimizer in this case, we're just reverting to a stochastic gradient descent. And that typically is a little worse than an atom optimizer or some other optimizers. Stochastic gradient descent is sort of like the base model, if you will. But we're just using that as sort of an example in this case. And the cross entropy loss, and I don't have a lot of time to go into this, but the cross entropy loss is essentially determining our loss in each class. So you could think of our outputs as coming out as sort of 10 outputs from our last layer, right? Our last layer is 10. And from each of those outputs, we need to determine the value of that output if it's determined in the class. And what we do is we essentially apply this loss function to determine, the highest value that it's predicting is, output number 5. We want to sort of reinforce that if it's actually the correct one, and then push the loss back for all the other ones. Okay, so that's essentially what that binary cross entropy loss is doing. And that gives us a loss function. And then you can see that, again, we're cycling through our epochs, and we're going through each batch, and we're enumerating through the train loader. And so that's going to give for each epoch now, we're enumerating through all 60,000 images in batches of our batch size. Okay, so for each 64 set of images, we're applying that now we're applying all these functions to that whole batch of images. Okay, so again, we're setting up the variable for the X and Y. That's the same thing we did last time. We're doing our prediction by passing X into the model, right? So this gives us the model here. We're not actually calling the forward pass, we're just passing that in, but that's essentially the default is the forward pass. So when we just do model X, that's calling the forward, passing it through, and it's giving us prediction. And now from that prediction, we want to determine how much the answer is off, and that's giving us that loss function. And so we're applying our loss function, which again, in this case, is a cross entropy loss on the Y prediction and the Y value. Okay, so this is the Y prediction and the Y value. That gives us an average loss. And again, these are just for our own sort of recording purposes. But then the other thing we're doing is just that loss backward in the optimizer step. And then this piece down here is just sort of pushing out the results of our output. And you can see if I go down here, my loss is getting down to a nice reasonable number, and the accuracy of the model is pretty good. You can see, so our loss is reducing down nicely. I won't worry about doing predictions on this, but you can imagine that we're probably getting to the 98th percentile prediction rates if we wanted to look at this. Again, this is just sort of looking at and setting up data examples. As we get into the other pieces, and I only have about 20 minutes, so I might just jump past this next one of the regression model. Yeah, so I do have another model here because a lot of people ask me a lot of times, guys that are working in oil and gas or other things, how can this be applied to tabular data, or how can we use this pattern on some of those models? So what I've set up here, guys, is another example using regression. What this is using is the Boston housing data. You can see I just set it up in a pandas data frame here and dumped it out. These are sort of the, I think there's 13 columns. I don't have the columns there, but you can see we're just using columnar data to do predictions, I guess, on the last column. And this is the model that's set up to do that. So if you want to look at this and you're interested in doing tabular data, here's an example of how to set it up and do that. You can see here is our model set up. It's a little more generic. We're not using a class this time. We're just doing some basic. We're just using the PyTorch sequential model, which allows us sort of to stack these layers on. You can see I'm just adding the ReLU functions on top of the layer. And the last function, or the last activation function here is the sigmoid. And the sigmoid is just pushing that output to between 0 and 1. And that just sort of gives us sort of a better value for how it's fitting across. And you'll see we start here with some really high losses. So it's really predicting, essentially what we're doing is trying to predict house prices based on factors. And you can see that our prediction model gets pretty good at the end. And if you're doing data science or you've looked at sort of tabular data for other models, you'll be able to sort of apply this, I think. Okay, so I'm not going to spend too much more time here, but I do want to get into, let me just go back to the PowerPoint. Okay, so what we really want to get back to is unsupervised learning, because a lot of what we're going to be doing with generative modeling, and this whole prelude is to getting up into how we do generative modeling, is to look at unsupervised learning and other sort of advanced methods of learning to do these predictions or these sort of generated predictions from out of nowhere or from the old machine's own mind, essentially, if you could say that. Okay, so what we want to look at is an example of the autoencoder. Remember, the autoencoder is we're taking one of those MNIST data set images, we're encoding it down to some middle representation that's a lot smaller. So again, we can think of this image as 784 inputs we're feeding into the model, and we might push that down to just a vector of 16. Okay, and then we rebuild that up and using the decoder. So the encoder and decoder are almost mirrors of each other, you can think of. They're just sort of flipped around. We'll look at the code in here in just a sec. But the purpose of this is sort of giving you a latent or hidden representation of what that sort of output is. And based on this hidden representation, you can actually use this as sort of doing principal component analysis or even finding cosine distance to batch your images together and look at features or similar features. And this is a common model we'll look at for a number of deep learning applications, but applies extremely well to generative modeling. And when we look at GANs and stuff like that, we'll look at and understand that the autoencoder is just sort of a split GAN in the middle and reversed, essentially. We'll talk about that again next time. So here's the exercise we looked at last time is the autoencoder game, and this is the challenge we had out, and this is the one that Dave did well on. And what I'm going to do, Dave, is just show your spreadsheet quick. Okay, so here's the spreadsheet, the Excel spreadsheet Dave gave me with his 160 solutions. I'm going to still go through this, but yeah, so in that simple autoencoder game that we looked at, there is a whole bunch of solutions. I never proposed or thought about doing this, but awesome job, Dave. So you'll be collecting the bounty for sure. But yeah, so I'll be looking at that and going over it. But that was sort of the example we looked at. If I go back to the PowerPoint. So that was the solution for the weights and the activation functions in the autoencoder game. Okay. And then this was one simple solution, but as Dave showed, there's a lot more solutions, obviously. Okay, so what we're going to look at here, we only have a few minutes left, is the autoencoder with PyTorch. So let's just jump back. Okay, and this one takes, well, I'm not going to run it quite yet. Well, yeah, I'll let it run in just a second here. Again, so we're doing a lot of the same imports. You'll see here, this time we're actually going to be importing the fashion MNITs. which is again similar to that handwritten MNITs digits data set. But the fashion MNITs define sort of 10 clothing types that has images for them and sort of gives classes for those clothing types. And it gives us the ability to either classify them, or as we're going to look at in this example, to auto-encode them and then rebuild them. And here's our helper functions, again, image show and toImage. And here's our hyperparameters, again, epochs, batch size, and learning rate. You can see our learning rate here in this case is 0.1%. And then simple transforms, again, it's the same transforms we've used, or similar transforms that we used before. Again, we're just sort of normalizing our data. The data we're pulling down here, so we're only going to pull down one data loader. We're not going to worry about a test data loader, because necessarily have to worry about that in Autoencoder, at least not for this version. This is where we're using the iterator again to go through the data loader, pull out a batch, look at that batch of images using make grid. And you can see the difference here is I just pulled in make grid a little differently using this syntax rather than using the whole definition. So I just sort of pulled it in as an import called make grid from the module itself. That sort of makes that code a little cleaner. And you can see here's the batch of that first batch of images. Again, we're using a batch size of 64. So it gives us a grid of 8 by 8 images. You can see here what each of the images looks like. Okay. Now here's our autoencoder model. And it's a little bit different because we actually have sort of two models, two separate models inside our larger model that we're going to connect. So the first part we set up is the encoder, which is going to take, again, a very simple sequential model. This is similar to our MNITs classification with the handwritten digits, where we're taking an image of 28 by 28. This time, though, we're sort of drilling it down to 128 neurons. Remember, from our previous example, we had 500. Again, that sort of comes back to the other question we had, how to sort of feel these things out. A lot of times it's just, just play with these numbers, determine if you're getting better results or poorer results, and that's really the best way to sort of modify them. There is sort of other ways, ML, AutoML, and other methods you can use, but if you're just doing this by yourself, just modify the number of perceptrons. Again, you can't modify the inputs in this case because the inputs have to match the image we're pushing in. And you can see this is a little bit different how we're structuring this. So we're setting the first layer, and then we're setting the activation function, Raylo activation function, and then we're adding another layer. So again, we're drilling this down again to 64, and then we're adding another activation function, another layer, again to 12, and then we're taking it down to another layer from 12 to 3. So we're essentially taking our image of 784 pixels, and we're drilling it down to a vector of three numbers. Okay, that's what we're reducing the image down to 3 numbers, and then we're going to feed those 3 numbers into the decoder, and the decoder is essentially going to do the opposite process from the encoder. And so you can see that we're starting with sequential, and we're starting with our 3 inputs, which will be coming from the decoder here. And we're again just building it up. So we're again just going to do the reverse order and just rebuild it all. And then using the linear, we're going to rebuild it all. And again, we're just going to, we could very simply do 784, but 28 by 28 works because it's a little more self-explanatory. And then again, in this particular example, our output is going to be a tan H activation function. And that's because our inputs are from -1 to 1. And you can see there, here's our prediction function. And this is how we sort of stack things up. So you can see each of our models are sort of encoded in, or sort of packed into our encoder or decoder. And then we just sort of pack the input into the encoder. That input comes from the encoder and then goes directly to the decoder, and that gives us the result. So that gives us sort of the whole pass through the whole autoencoder, if you will. Okay, and again, we're just going to use the model of autoencoder. Loss function is going to be a simple mean squared error, essentially just a very simple subtraction model. So the output of our images, we're just going to subtract from the input images. We're just going to do a raw subtraction of pixels. And based on the subtraction of pixels, we'll determine the amount of loss. So if the image is giving us a really bright area in one spot and it should be really black, there would be a high loss. Or if the image is really sort of matching the colors it should be at a particular area of the image, then it would have a really low loss, right? Okay, so again, this is where we're doing the image view, and this is only because we're sort of managing our data as a single layer. Again, this will change as we move up to more advanced methods. And all of this, again, is very simple to what we've seen in previous examples. And what I've done here is I just interrupted. So what I'll do is I'll run all this again, and we can see what the output is going to do. And this will actually produce the output as it's training the model for every epoch. And I don't think it has to download the data again, so it should go pretty quick. Okay. So here you can see the output. So this is actually the output, the decoded output. Now remember, the really impressive thing here is that we're reducing this down to just 3 numbers, right? 3 numbers at the middle piece, and then we're rebuilding the image up. And those 3 numbers, we sort of looked at or plotted those numbers into sort of using cosine distance or other sort of form of determining distance between vectors, it would really give us our clumping of our numbers really well. Okay, and you can see this, it's really giving us some really good results quite quickly, actually. So we've got this set for 100 iterations, but this we're only currently on the first iteration, and you see it's giving us pretty good results in most cases. You can see in some of the more difficult things like the bags or the sandals or shoes, it's having more problems, sort of predicting what those should look like. But the shirts and stuff like that are really coming out quite nicely. Okay, any questions on this stuff, guys? I went really fast, and we're already. Yeah, so the variable X, variable Y, turn those into PyTorch tensors on the CPU. That's the reason why they're there. There's other ways we'll look at how to sort of apply those as we look at other advanced models, but that's just the reason why they're there. That's the reason why I always put them there. So this week's coding challenge will be for $100, and the winner will be the one that achieves the lowest loss. And you can only change the hyperparameters of learning rate, batch size, and neurons. Oh, excuse me. Let me just go back through what that means. Okay. So all you can modify in order to get that is you can't change the epochs. You want to keep them at 100, but you can change the batch size or the learning rate or the number of neurons in the model. So you can change all of these. Aside from this, the 3 has to stay. Okay, so you want to keep the 3, but you can increase the size of the model. You can increase this to 256, 500, or whatever. The only thing that has to stay is the latent dimensions of 3. You want to keep it at 3 because if you increase that to 32, you could easily increase the answer because it just gives you a lot more room to figure out what that number is. Okay, so any questions on this stuff, guys, before I leave you with that? And did I go too fast, or is everything okay? We're pretty much at the end here, and question round has begun, so go ahead. Nobody?
There's some questions in the chat.
Can you have a variable Z? Yeah, absolutely. You just have to declare a variable Z. Yeah, we'll look at some other examples where you use variables like Z or stuff like that as well. But yeah, variable Z is sometimes referred to as the latent dimension. Or could you have 3 dimensions? Well, that's, so what we're looking at is not really dimensions as so much as groups of data. So the X and Y, let me just, so I just want to make sure. In this particular case, I'm not sure which one you're looking at there. So the X and Y in that case are just, the X is always sort of the inputs and the Y is prediction or the outputs of the value. We'll often refer to Z as the sort of latent dimension or the hidden dimension in many cases. So we'll look at Z, for instance, in a variational autoencoder or other models where we'll sort of look at a value that we need to, or what we'd want to predict for Z. I'll get to that later. We talk about variational autoencoders, but that it's just sort of a different way of using the autoencoders as a way of not just learning the three numbers or how many numbers you want, but essentially how the data is distributed in the image or how the data is mapped in the image, essentially. Any other questions, guys, or did I miss all the questions? Yeah, so how is the loss encoded in an autoencoder? Okay, so and this is the tricky part that most people really don't sort of, it's so simple that it's sometimes not so obvious. So if say, for instance, we take this image here of this sandal, okay? And if our input image is this image here, say this sandal here, or well, something looks, all the same. What we're essentially doing is taking the one image and putting it on top of the other image, and then seeing how much, essentially subtracting the one image from the other, and the amount of subtracting from the actual values of the image. And remember, the brighter values are like 1, and the darker values are like -1 or 0. If we're only doing values from 0 to 1. That's where we go back to the autoencoder game, for instance, or the Perceptron game, where black represents 0 and white represents 1. All we're doing is subtracting those two values together, and that determines the loss. And that loss is being applied to each of those sort of pixels across the network. We average that loss and apply that back. And just through that process, this is what our network is learning. Just by taking that pixel minus pixel value and returning that loss back through the network. And it's just learning how to generate that. Now, the advantage here is that it's not sort of generating a blind, it is generating on something, but it's only generating on those three values. There's only three latent variables that we sort of decrease or encode our representation down to, and then we rebuild it with the decoder. When we get into other generative modeling techniques, our generators will generate from random data, entirely random data, and their whole learning ability will to be able to match or understand or how to map to what the other model is sort of discriminating or critiquing against. Okay. Yeah. So it does compare it with it compares it with the input gets compared with the predicted output, or what the sort of autoencoder passes through in the last step of the decode. So this output here from this last piece is actually what it's doing the comparison against, and that's what it's calculating the loss on. And like I said, it's a simple matter of just mean squared error loss. So it's essentially just doing subtraction from the pixels, from one set of pixels to the next set of pixels. And just based on that subtraction, we're getting some really, and as you can see, as it's running, it's getting much better identifying even some of those harder to define things like the sandals and the shoes.
Michael, I had a question on the minced model, the numbers data.
Mm-hmm.
So in the first fully connected layer, it takes a 28 image, and it automatically flattens that, versus as like in Kira's, you go from a convolution to max pooling to a flattening layer.
Yeah.
But this linear, just because it's the same as layer 2 and layer 3 are the same PyTorch functions, so it just will automatically flatten that.
Yeah, that's essentially the reason why we're doing that is, so when we'll look at convolution next time, but with convolution, you can feed in a 2-dimensional or a 3-dimensional set of data, and the convolutional layer can accept that. but sort of a linear layer can't accept that two-dimensional piece of data. That's why we have to flatten it. But the disadvantage of flattening that data is, we're taking that image, we're essentially flattening it, right? We're not even, we're essentially unrolling that whole image as a string. And we're going to lose a lot of context between different pieces of the image, and that's where convolution comes in, and that gives us a really big advantage, essentially.
Yeah, I guess maybe where I'm lost is where is that image being flattened in this? So I'm looking at Gen 1 classify PyTorch. So where, and I guess it would be similar in the.
Yeah, it's the same here. So essentially, when so the transform is essentially doing that. It's this piece here. I can type that out as 784, which is the same way of saying that that's flattening that whole image down to one single vector, right? Okay. So just by putting 28 by 28 is just sort of a helper for us to say, yeah, it's a 28 by 20 image that we're feeding in, but it's actually flattened 784 pixels. So that flattening piece happens in the transformation itself, actually. So here, this piece. So this piece here, that's the piece that's doing the flattening.
Oh, okay. You built the model and then you transform it before you fit it in, send it into the model at this point. Okay.
Yeah. So, and that's really all we're doing is, and as we get into sort of convolution and other things, we don't have to do that. And that's why I said this is sort of a special case in here, because a lot of times we won't necessarily need to do that if we're using higher layers. And Keras makes it a lot easier, I guess, in some cases to add convolutional layers. PyTorch also does, it just handles them a little differently. So I just wanted to go over a little differently. It's going to take a little more discussion, I guess I can say. Loss equals loss function y prediction minus the x image. That's where the magic happens. Yeah, the question was, where is the magic happening? The magic happening is right here. So this loss function is essentially just taking what the image prediction is, and it's subtracting it from what the image actually is, right? So we can think of it as, this is the image coming in. Whatever it's coming back is decoded. Say this is coming back as decoded. If we take and subtract those two images, just the raw pixel values, right? So we can think of pixel values as numbers, right? From 0 to 1 or 0 to 255 if they're just bytes or whatever. And all we're doing is subtracting those values, and that becomes a number that we're pushing back as a loss through the network. So it's just a really simple, subtraction. It doesn't seem like that, but it really is that easy. I mean, subtraction and then doing an averaging and square, essentially. But, it is really the basis of just a simple subtraction, essentially. Any other questions? Okay, good. Okay, so remember, guys, $100. If you can beat the loss for what this model comes out to in 100 epochs, just by training or tuning the parameters of batch size and learning rate and the neurons themselves. But again, you can't change this last one. Any other questions? Comments?
So the output of this model, will this be saved back into the GitHub? So we open it, we can see what its loss is.
I'm not sure. Can you just repeat the question?
Well, so because these things are random, right? Every time you run that, if you have the same parameters, you'll get slightly different loss after 100 epochs. So, I mean, if the version of that, I think, if I still have it open, but it Yeah, there was a loss of 0.0816 in the version that I opened up from your GitHub.
Yeah.
So this one, I mean, I guess it should come out. Well, I don't know. Maybe come out close might be different.
Well, but I mean, for those that are sort of partaking in the challenge, it would probably be an order of magnitude different. But but you have a really valid point. I mean, keep in mind that every 64 batch we're pulling from the images, and the reason why we use a data loader is they absolutely are, as you mentioned, randomized, right? We want them to be random batches of images that we're pulling through as 64 images. That gives us a better averaging. So there will be sort of a minimum loss, and you can see the loss might bounce around a little bit. But I'm just saying, after 100 epochs, what can you stabilize the loss to? And there will be, we can look at the history of this and see how it stabilizes, and you can do the plot history, and that's, I've left that up to you. You want to look at that. There's plenty of examples in those previous code things. But see how the history of the loss sort of approaches and what factors that affect that. So I'll leave that up to you guys. You can see here that it's jumped up to 0.1, for instance, right? And that really has a lot to do with, so a lot of what the loss might be affected by is these sort of side little images, the ones with the extra detail and stuff like that, that might be harder to sort of find or average out, especially with some of these classes that are very diverse, like sandals. There's very lots of different variations in sandals, for instance. So, you know, what is it sort of the model? Do you have to increase the size of the model? Do we have to use more neurons? Do we have to change the batch size to get better results? You know, what is there a way, how can we sort of reduce the loss? Now, 0.08 seems like it's fairly small, but we can go much smaller. So, any other questions? Okay, guys. Thanks everybody for coming. And if there's no other questions, thank you very much, guys. Okay, have a great night.
Thank you. Have a good night. Bye.
To finish up, how to start this.